Good evening, ladies and gentlemen. I am Dr. M. Chakraborty, HOD CSE, KCG College of Technology. It gives me an immense pleasure to extend a very warm welcome to all of you present in this third Digital International Webinar Series. On behalf of the management, principal, faculty, and entire student community, I would also like to welcome and express our gratitude to our esteemed speaker, Dr. Shounak Chakraborty, Professor CSE, Norway University of Science and Technology in Norway, who have accepted our invitation to present Energy versus Performance in Modern Computing. Once again, we welcome you, sir, to our KCG portal. Now I request Dr. R. Dhanlakshmi, Professor CSE KCG, to introduce our today's speaker. Over to Dr. Dhanlakshmi.
Good evening to all. Thank you, sir. It's my pleasure to introduce our guest speaker today, Dr. Shounak Chakraborty, to you all, who is going to talk on modern computing, energy versus performance. Dr. Shounak is currently associated with the Department of Computer Science, NTNU, Trondheim, Norway, as a postdoc researcher. Prior to his joining at NTNU, Norway, Shounak earned his Dept degree from Makat Maulana Abdul Kalam Azad University of Technology and ME from CEG Guindy, and his PhD is from IIT Guwahati, and after completing his PhD, he has joined as a postdoctoral researcher, and he has been working as assistant professor in IIIT Guwahati for a year, and later moved as a postdoctoral researcher in NTNU, Norway. Primarily, his broad area of research is computer architecture. However, specifically, his research interests include high-performance computer architectures, power-efficient memory systems, and thermal-aware architectures. He published several research contributions in AC and IEEE transactions and elsewhere. He also serves as a reviewer of reputed journals like Supercomputing, Springer, and ACM Transactions in embedded computer systems, etc. He has obtained several travel grants for attending conferences in India and abroad from ACM, IEEE, IFIP, etc. For his next research project, Tectonic, he has been awarded with a Marie Curie Individual Fellowship grant in 2020 from European Commission. Thank you, Shounak. It's a pleasure to have you here, and I welcome you to the stage, and the podium is yours now. Thank you.
So thank you all for your invitation, and I'm really happy to see you all here today. So are you able to see the slides here?
Yes, we can. Yes, we can. It's okay.
Yes, sir.
Okay, fine. So good afternoon, one and all. So today's talk, so it's actually modern computation, energy versus performance, as you told earlier, as it's the title of the seminar. So myself, Shounak, I'm a postdoc researcher at NTNU Trondheim, Norway. So before getting into the deep of this talk, so I'd like to say you that as I'm doing research on computer architecture over the years, last 5-6 years, so it's actually I'll more talk about from an architect's point of view. Well, so before getting into the details, we'll first see what a chip multiprocessor is. Practically, chip multiprocessors are the basic building block of the modern computers. So in modern computing system, if you just open it up, you will see that this is the processor chip, where in this case, you will just find it out that we have an Intel Core i7 CMP on the right-hand side of this slide. So where you can see there are 4 cores. The name itself implies that you have multiple processors in a single chip, which is called as chip multiprocessor or multi-cores in modern era. There are 4 cores here. Each and every core is equipped with its local L1 and L2 caches, along with a shared cache on chip. You can see the shared L3 cache is shared among all the cores, which actually occupies one of the most significant area on this wafer real estate. The transistors, the basic building blocks of such chip, are actually the atomic unit of the CMPS, or also can say, so whose channel length is actually day by day is decreasing. So channel length is practically the simple thing is that this is the length between the source and drain. So this channel length is decreasing with the advancement of the VLSI technology. As per the Moore's law, once your transistor's length is decreasing, in the same area, you can accumulate more number of transistors. And as a result, you will get huge amount of performance benefit from such CMPs or chip multiprocessors. But there was a problem. You have accumulated more number of transistors on a single chip that may drastically improve or increase the power density on chip. Another scientist called Dept, who has given another kind of theorem where you can see that it's called actually Dept scaling, where he talked about the decrement in channel length actually reducing the delay of the transistor. As a result, you can increase the frequency of your underlying hardware or underlying cores. So processing frequency was gradually increasing at the very beginning of this current century, but unfortunately at the time of 2004, 5, and 6, suddenly the researcher and designer, they stopped increasing the frequency. So what are the primary issues? The primary issue was that the power density was going up. As a result, it was actually ending up with huge increment in the heat dissipation. This heat dissipation practically increased another problem called as subthreshold leakage current, which actually flows in the reverse bias. And this leakage current further improves the temperature of the chip. And as a result, your chip may burn out. So to address this issue, before that, we'll just look at the power consumptions in a CMP. So power consumption in a CMP can be divided into a couple of parts. One is on the left-hand side, you can see it's dynamic power. On the right-hand side, we have the static power, which is actually called as also leakage power. On the dynamic power front, so you can see that the dynamic power practically increases just because of the capacitance. You have the voltage and you have the frequency just because of this. So practically dynamic power is called dynamic because of the heavy circuit activities, it's being increased. So on the other hand, if you have the static power, where your power consumption depends on the temperature and the supply voltage. And with the temperature, you can see the quadratic relationship is shown here. So T represents the temperature, where V is the supply voltage, and C on the dynamic power represents the is representing the capacitance of the underlying circuitry. Out of all on-chip components, as you have shown here earlier on my previous slide, the cores are practically well known for their huge amount of dynamic power dissipation or consumption, whereas the caches are well known for their huge amount of leakage power consumption. And out of all power consumption of the caches, so static power or leakage power is excessively high. This is one of our empirical results that I have developed during my PhD. Additionally, this huge amount of static power consumption makes the cache memories as one of the principal contributor of the total power consumption of the chip. On the left-hand side, you can see the table where I have shown you the six basic CMPs that we are using nowadays. So where the power consumption by the cache memories are really, really high. And that motivates the researcher and the designers to reduce these numbers. So what are the thermal issues? So practically, we have the leakage of static power and dynamic power on chip, which is the total power consumption by chip, and that power consumption will increase your temperature. This stimulation in temperature, maybe average, maybe peak temperature, will further increase your leakage power. Thus, it forms a circular dependency. This circular dependency may lead your system to thermal breakdown, which is a big catastrophe for underlying circuitries and real threat for the system as well. So to address this issue, you first know which are the primary elements who actually creates the hotspots on chip. Cores are the hottest on chip elements out of all on chip components, and they create the hotspots on chip. Additionally, the cache memories, which were earlier the colder on chip component, but in modern case, when your transistor size is very less, that is the channel length is lesser than 32 nanometer or less, your cache will become a potential candidate for generating hotspots on chip. And high temperature across such large area of the cache, they can consume huge amount of leakage power. So how to mitigate this issue? Power versus performance, right? So fixing power budget at design time is a very, very well-known industry practice. And performance constraint power optimization, which is the main title of the modern computer science, computer architecture research, has two parts. First one is at the cores, you can apply DVFS or DPM, where DVFS stands for dynamic voltage and frequency scaling, where DPM stands for dynamic power management. So you can dynamically change your voltage and frequency of the core, where in case of DPM, you can just shut down or get a particular processing core to reduce the power consumption as well as the temperature. Additionally, for the cache-based policies, we have a couple of policies. One is the state destroying policy, and another is the state preserving policy. The former one practically evicts the cache block from a particular bank or particular cache area, and it just shut it down. So on the other hand of the state preserving technique, you can have you can have the data on the cache while you are applying some power optimization. You just reduce the voltage of a particular domain of the cache, and your data will be there as it is. Just to preserve the state of the data, you just reduce your voltage up to a certain level. That actually being achieved by using some multi-threshold CMOS circuitry on chip. So, however, in this seminar, so I'm not going to details of the very much about the circuit technologies. So rather, we are focusing more on the cache-based some policies that I have developed during my PhD, followed by one recent policy that I am developing, still developing. Yes, for the 3D chip, and also last year I have developed for a 2D chip, heterogeneous processor, along with the caches. So that core-based ones I will also discuss with you very briefly. So now we have some jogging on our memory. So what is some primary cache characteristics? So as we are going to see some cache-based policies. So first of all is the locality of reference, which is of two types. So practically temporal locality as well as the spatial locality. The temporal locality practically says that practically when you have the one data block which is being accessed currently heavily, so that data block will have the heavy access in near future. On the other hand, if you look at the spatial locality, you can anticipate that your heavily used portions, neighbors, or the adjacency blocks, or the adjacent blocks, they will have also the heavy usage in near future. From this locality of reference, you can come up with a cache that will have the non-uniform distribution of the cache accesses. This non-uniform cache accesses will motivate us that you will have some portion of the cache, those have the underutilized, those are practically underutilized. So such underutilized portions you can turn off to reduce the leakage power consumption of the cache. Additionally, when you are looking at the core's characteristics, you can see that the CPU registers that are those are just attached to your pipeline of the core. They are also well known for their huge amount of hotspot generation that actually stimulate the peak temperature of the ALU, CU, as well as the other underlying circuitries attached to the core. So cores are they are very much well known for their hotspot generation that will actually stimulate the peak temperature due to its huge amount of dynamic power consumption. So practically my research objectives during PhD and right now is that, so shrink your on-chip LLCs dynamically to reduce your leakage power consumption at multiple granularities, that is maybe at bank level or as well as both at bank as well as OA level. And through this, what I'm going to achieve is that I am reducing the leakage power. Additionally, this turned off cache portion will generate some thermal buffer on chip, and that thermal buffer will actually exploit the superposition and reciprocity heat transfer theorem, by which it will reduce the peak as well as the average on-chip temperature. As well as I am also targeting to reduce the peak temperature by more effectively applying DVFS on core. So this talk outlines is like that. So first of all, I'll give you some brief about the baseline architectures and the caches and the cores. And additionally, I'll say you something on the motivation, followed by the simulation methodology, which plays a vital role in case of computer architecture research. DICER is the next, which is practically my PhD thesis. And there are 4 contributions. I'll just give you very brief idea on that because it may be a bit boring. So let's see. Well, so followed by a core-based policy, that is WaFFLe, that I am working now, that I have just worked. That work has been finished in last August or September, and this work is still under review. And I will give you some brief about my ongoing and future projects at the end. So that's what is our baseline architecture. So on the left-hand side, you can see one tile CMP architecture. It's called actually TCMP architecture, where the chip contains 16 replicated tiles, where each and every tile contains a code along with its multi-level caches. So that is and here you can see that one is L1 instruction cache and one is L1 data cache, and they are local or private to the core. Additionally, we have one chunk of L2. That L2 is actually numbered here 13 just because to represent just the tile. So it's just simple nomenclature. So I'm not going to the details of anything. And this L2 is actually divided among all the tiles, and each and every part of this L2 or L2 slice is called as L2 bank. And all of the L2 is actually physically distributed, but logically it's the same L2. So any core from any of the tile can access any of the L2. So it's completely shared among all the all the cores, right? So from zero can actually access data from its own L1 tiles, but it can access data from any of the 16 L2 banks. So they share the address spaces altogether, right? Additionally, if you look at this processor, if 0 wants a block from its home tile, home L2 bank, then the access pattern, the access will be very easy because the data is available on the home block, so the access time will be very less. When 0 will try to access the data from 14, 15, or 11, so some other tile, it has to traverse all the way 5 or 6 hop so that its access time will be increased, right? So this kind of non-uniformity exists among these L2 bank accesses. So such kind of architecture is known as the NUCA or non-uniform cache access architecture. And once your data, all appearance of a particular data block is fixed at some particular location at the cache, it's known as the static NUCA architecture in this case. We also have the dynamic NUCA, so I'm not going to the details of the dynamic NUCA or DNUCA architecture. On the right hand side, you can see the whole tile is actually divided, whole chip is actually divided into 2 parts. On the periphery, we have the ports numbered from C0 to C15. We have 16 ports on the periphery. And inside, at the centralized location, we have the 64 banks numbered from 0 to 63. So L2 is shared among all ports here as well, like our TCMP architecture, but they are placed at the centralized location of the chip. Now, all of these cores in both of our architecture, they are homogeneous in nature because they have the same amount of VF settings and other things. They have the same processing power. They have the same everything is same. So it's called actually homogeneous architecture. So you can also look at some heterogeneous chips like the ARM's Big Little architecture is one good example of such heterogeneous chips. So where you have the different types of cores, means some cores are very much power hungry, but they are very much give you the benefits to your performance. On the other end of the spectrum, you can have also another set of cores, which are also known as the little core in this case. So they are very much power efficient, but they are slow in nature. Well, so what motivated me at that time when I was trying to develop some cache-based technique to reduce the leakage power consumption and the temperature. So on the top, we have the couple of graphs. So on the left-hand side, you can see that the cache banks, as we have talked about in my previous slide, is they have diverse set of usage statistics. Some banks are used very heavily, where some banks have very least amount of usages, right? On the other end of on the other side, you can see when you have the 64 banks on the right hand side, I have also the same pattern, that is the diversity exists among the cache bank accesses, right? And as we know about the locality of reference, the banks will have the heavily used in current time, will also have the heavily used in future. So depending upon that, if we can shut down some least used bank, definitely you are going to get some benefits in terms of power consumption or temperature, but you have to be very much careful about the performance, because least used bank will have least used at the moment, but in case of some long running application, this may not be true. And the bottom graph, where you have the 16 banks numbered from B0 to B15, for our tiled architecture, we have shown here that some banks, they have the very much least used in earlier epochs, that is epoch 1 to epoch 2, epoch 1 and epoch 2. They have the huge use, they have the higher usages in the in your later time of the execution, that is at the epoch 3 and epoch 4. And the reverse results is also you can find for the B12, B13, B15, B14, all those banks. They have the heavily used or the huge usage during the earlier cycles of the execution, but in the later time they have very least amount or the almost zero usage, right? So practically in long running application, what we can see is that the locality of reference is practically violated. But for the small time frame, it's okay. But for long time frame, this is not okay. So locality of reference is violated for a set of modern long running applications. Keeping this in mind, additionally, another thing is that inside the bank, when you just drill down the bank, you can see we have the sets, we have the ways. There also this diversity exists for the accesses. So we also have the non-uniform access pattern to the sets as well as for the ways. When you are resizing the cache, you should consider the performance, because performance is the major thing that we are going to achieve, right? So when you are reducing the cache size, it will increase the capacity and conflict misses inside the cache. So there are 4 types of miss when you are using the multi-cores. it's actually called 3C or 4C. 3C was for the compulsory capacity and conflict miss. That is for the your single core system. For your when you are jumping to the multi-cores, you have the three kind of you have additional miss. That is called actually coherence miss. So practically, when you are reducing the cache size, you are going to increase the capacity and conflict misses drastically. So even if it is the least used portion in some cases, right? Because least used portion may become a heavily used part in the cache. So reducing cache size will drastically increase the MPKI, called misses per kilo instruction. That will have direct impact on the IPC, that is instruction per cycle. You can see the IPC is degrading, that is instruction per cycle will be reduced, that is your performance will be degrading once you will have lesser amount of cache. That is on the fly, if you are just reducing the cache size, you are going to lack some performance. So how to cope up the situation? Additionally, the thermal issues in LLC. So what are the thermal issues in LLC? Because you have the more number of transistors, you have accumulated more number of transistors in the cache area, that will actually results into increment in temperature, not up to the case like not the exactly case like the cores, but definitely the caches also are prone to increase the temperature in some certain up to some certain level. You can see on the top couple of graphs, so where I have shown you the how leakage power of the cache is going high with the temperature, and also you can see the peak temperature of the LLC on the left hand side, and how much they are contributing to the total power consumption of the chip. So with the gradual increasing in the size of the cache, the peak temperature and both the leakage power is going high. Okay, so now the core-based versus the cache-based thermal management. So on the left-hand side, we have the core-based policies. So core-based policies in modern system, people are mostly focusing on the DVFS and the task migration. What is DVFS? As I told you, the dynamic voltage and frequency scaling. This is based, these DVFS-based methods actually aggravate the system performance by reducing the running frequency of the cores and incorporating switching overhead. So switching overhead practically incurs just because of switching the voltage. But for the frequency can be changed abruptly, but changing the voltage from one level to another level has some timing overhead, right? So how to cope up this situation as well, because people are frequently they are using the DVFS in lots of modern systems, right? So another most significant part is the task migration. So task migration is a very well-known technique that is used mostly in case of the real-time systems, so where only when it will be applied when you have the number of tasks are lesser than the number of cores available. So why like that? Because you have to migrate the task from a hotter region to a comparatively colder region on chip, and for that you need some cores with some cores should be free. So where you can move your task from one part to another part. But this task migration is also very prone to degradation in performance. So this may be a big loss for the system if you just doing it very much. If you're going to exploit this task migration very frequently, this is not very much performance friendly. However, this core-based technique practically they directly impact the peak temperature of the chip. It will reduce the peak temperature. On the other hand, if you look at the cache-based policies, you can see computing is not affected directly, but decreasing in cache size will definitely impact your performance by increasing huge amount of off-chip accesses, because your miss rate will be your number of misses will be increased, right? It's also effective in case of the larger on-chip caches, and this can also have enough potential to maintain a low average temperature for a longer time span. And by that will happen just because of the exploitation of the superposition and reciprocity theorem of heat transfer. Simulations plays actually a major role in case of computer architecture, because we are not allowed to use the real hardware because we are not the practical hardware guys. So like electronics or physics people. So simulation is a well-known platform for computer architecture, which actually provides us or helps us to validate our ideas, right? So in our work, in my work I use this simulation framework I have shown in here in the diagram. You just look at the diagram. So where you can see the Simix plus James, that is a performance simulator. It's actually a full system simulator where you can actually install your own OS. That is, I used to use the Solaris platform on the bare virtual hardware of Simix, whose architecture will be provided by the James. And James is a well-known simulator in computer architecture community. And from where you can get the performance traces that will be fed to another simulator, MacPet, which stands for multi-core power area and timing simulator, from which you can collect the area and as well as the power traces. The power traces will be fed to another simulator, hotspot. Hotspot will give us the temperature, and these thermal simulations will give us the steady state as well as the current temperature of the element, and that temperature will be sent back to the performance simulator for your next thermal management policy. The area is also collected from the MacPet simulator one time, and that area will be used by the hotspot through a chip floor plan interface, so which will give you the practically the adjacency matrix of the all on chip components, so that you will your simulator will know that how your heat transfer will happen among which elements on the chip. So dicer, before looking into the dicer, we'll just see some migration mechanism. So what I have done practically, so that's what I have implemented in GEMS. So suppose we have two banks, just consider two random banks, one is the victim, another is the target. So left top is the victim bank. So victim bank, we assume that we have the very least used bank is victim, and this victim bank will be turned off shortly. So before turning it off, as it has some data that needs to be evicted. How to evict? You can just simply invalidate, or you can simply write them back. If it is dirty data, so you have to write them back. If it is clean data, you have to just invalidate. But if you're turning them off, you have to consider all of them to prevent the data loss. So what you can do, you just write them back to the main memory, or you have another option to transfer to some other on-chip location. We have chosen the latter one because writing them back to the main memory will be very, very much prone to degradation in performance, because off-chip access will be very, very much costly, because more number of cycles will be there in the system, so that will actually give some huge degradation in performance. So as per our empirical analysis, we found this problem. So we decided to put it some other bank called target. So we'll have the data movement like this. So one by one, you just move the data from victim to target. Once this is done, now you turn it off. Once you have turned it off, as you are using the static NUCA, so how to manage the data in future? So from now onwards, if any data is coming to this, particularly this turned off bank, will be sent to the target, and target will be handling your request in future, right? So this is actually known as the forwarding of request to the target. So now, if you need to turn it on to provide more cache space to your application, because your application's performance is going down, so to cope up the situation, you need to turn it on. So the reverse thing will be happening now. So what will happen here? So all the data blocks will be again transferred to that victim that was turned off earlier. Now you back to the normal operation after turning it on. After moving all the data, those were actually transferred from your victim to the target earlier, and you just send them back to their normal location. And now you can simply proceed with your normal cases, right? Well, so execution will proceed now. So now now I'm dipping inside that. Now I'm just looking in the dissect. So this is there are a couple of parts in my thesis. So on the left hand side is the static energy reduction. So reducing the cache size will definitely give us the benefit in case of the static energy, and as well as we can improve the thermal efficiency. So at cache bank level, so what I've done is that, so first we are going to shutting down the least used banks, and that's obviously a promising option. So for reducing the leakage energy without affecting the performance much, as well as the remaining power down banks, they will handle as a target bank the loads of these turned off banks. Well, so, and while we are doing this, we have done this empirical analysis earlier, so that I have told you in the last slide, that is on-chip migration is obviously better than the write back. Now this is called the BSP. So this is the basic bank shutdown policy. So in basic bank shutdown policy, you can see what I have done. So first you collect the IPC, that is the instruction per cycle, as a performance parameter. So this just looking at the parameter periodically and looking at your number of turned off banks, which should not cross a certain limit, because you need the least amount of cache space to cater your current application. So towards that, you have to consider the number of banks turned off as well as the IPC. So once they are within some certain limit, so you cannot turn off some bank after doing some relevant migration to the target from victim. But according to our observation, too much shutting down, that can reduce definitely a lot of leakage power, but definitely it will curtail some performance. So, and additionally, the application size that will be changing, keeping on changing in future. So how to tackle this problem? So we actually went to the next step, that was the actually resizing of cache, that is turn off and turn on. Both things should be allowed in the on your cache to resize it properly, right? So if your performance degrades much, you just turn it on. If more bank can be turned off, then you can try it, definitely, because your still your performance degradation is within some stipulated limit. So that's what is our algorithm. So on the left hand side, you can see we are just selecting the victim. Once our condition is satisfied, just select the victim. Then do the migration from victim to target. Once your migration is completed, then you enable remapping and turn off your victim. On the other end, you can see how we are turning it on. So just keep some flag on your on your target bank with some each and every data to just detect their original location, and now you just send them back to the victim. And once you have this migration is done, then you just disable the remapping and you just go back to your normal operation. So these are the couple of things. By utilizing this couple of turn on and turn off mechanism, what we have done, we have developed 3 policies. One is P1, one is P2, and another is P3. So P1 is practically unrestricted way. You just do turn off and turn on wherever you get some scope, right? But too much turning on and turn off will increase the forwarding as well as the migration on chip. That will practically reduces our performance. So IPC degradation was very, very much high. So to address this issue, what we have done, we developed P2, where we are initially allowing the turning off of the banks. But once our performance start degrading, we only allowed to turn it on. That is, only turn on will be allowed. But this problem also suffers from another big issue, because this policy actually has a problem, because it will not allow the turn off at the later cycles of the execution, right? So that time what will happen, in case if you have some least use banks, you are not turning them off, so you are not reducing the energy properly, or you cannot save the huge amount of leakage power, right? So leakage power reduction was very less in this case. So we jump back to P1 again, because P1 has given us very good amount of leakage savings. But this time we put some timeless restriction. We call it as P3. That is, for the first 25 cycles, whatever the first 25 million cycles, you do whatever you want. Any resizing will be allowed. For the next 25 million cycles, you do not do anything. You are not allowed to do any kind of resizing. Next 25 million cycles, you are again allowed to do, and so on. So like that, you just proceed. And we have employed the power getting circuitry, was given by Powell et al. In 2000. Early 2000 for such kind of for implementing such kind of dynamically syncable cache, and that's how our result is. So I'm just skipping this slide. So just look at this one. So you can see the significant amount of savings we have achieved for the leakage power as well as for the ADP. So as a summary, I can say that the remapping information is kept at the L2 controller. So we maintain the transparency at the L1. So we don't have any kind of overhead that will be incurred in the L1. And we have also used the reuse counter. So reuse counter is a very nice concept. So that we have used to break down the LRU problem at the target while doing migration. And we had the negligible storage overhead. So storage overhead was not up to the means very less actually. So you can just simply implement this one. Even the bookkeeping is also very easy in this case. And also transitive remapping was not allowed, because we are not allowed to disable any kind of targets, because target will not be gated. So, and next thing is that one bank can become a target of more than one bank, but reverse is not true, because you can only send all of the data from a particular bank to another particular bank, which is the target, but you cannot send them in some multiple location, right? Multiple banks, you cannot select them as a target. P3 shows the best result out of these 3, as it saves energy like P1 with the restricted resizing, hence the lesser degradation in IPC. Now there are some certain problems that we have encountered during implementation of this P1, P2, and P3. So what we have ameliorated through implementation of DAM. So DAM stands for Dynamic Associativity Management. So why we have done this? Just because of that, as an underlying causes, we have some certain issues. So more conflict and capacity misses we have encountered at the target banks in our last policy, as well as the sets and ways inside the target banks have a non-uniform access distribution, for which we are very much enthusiastic to apply DAM on that, to make the access distribution very much uniform, so that we can get more performance benefit. And obviously the target should be chosen with its minimum distance from the source or the victim. Towards tackling this one, so what we have done as the mitigation issue, so we have selected some moderate use bank as target first of all, to keep the misses within some certain limit. Then we have applied DAM at the target bank to improve the set utilization inside the bank, and we have done the distance cognizant target selection. These 3 policies, these 3 cases, actually they have helped us enough for improvement in the performance. So once your performance has been improved, now we have the opportunity to trade the performance to save more power by shutting down more number of cache banks and shutting down more number of cacheways. So what we have done here. So in this diagram on the left, you can see that we have the all sets. Suppose we have 8 sets in a particular bank number from 0 to 7, as well as we have 8 ways. Here we are dividing the all of these cache sets into two equal parts. That is 4 ways for the NT and 4 for the RT, and all RT parts of the friend sets. So friend set is a concept. So I cannot. The time is very less to discuss about this friend set because this is a nice concept. So developed in our lab in IIT Guwahati earlier. So one heavily used set can use the RT part of the others of his friends who are actually having the least used sets actually, right? So some ways from the least used sets can be utilized by some heavily used sets who are lagging behind some just because of the scarcity of space, right? So that kind of architecture is this one. It's called actually CMPS VR. So we utilize this one to improve the associativity, logical associativity will be increased of particular set, and thus we are going to improve the performance. Well, so I'm not going to the details of this one very much, so it will be a bit complicated. Well, so by utilizing all of this, so what we have got, so the EDP gains are really significantly high. That is 33 and 35% for this couple of policies. That is OS shutdown at the NT location and OS shutdown at the RT location. So here you can see that the NT location couple of ways we have turned off, and from RT also 2 physical ways have been turned off. Well, so the static energy savings is also very high. That is 68 and 70%, while our IPC degradation is not very high. It's also within some certain limit, less than 3% in both cases. DAM practically reduces the overhead caused by the cost due to the bank and OS shutdown, and turns on the cache ways if IPC degrades more than the threshold value, and it's obviously beneficial for the higher associative caches. Yes. Now we are jumping inside the temperature control into CMP first. So what we are doing here? So the primarily our contribution is like that. You just turn off the cache hotspots. So out of all cache banks, so the banks having the higher temperature, you just targeting them, and you are just going to shut them down, right? Additionally, the lightly used banks, they are consuming leakage power unnecessarily. So we are calling them as CB or cold bank, and those banks will also be turned off. Because when you are turning off a particular bank, having heavily used or least used anything, so it will practically have the almost zero power usage. That will actually reduce the temperature of that particular location, and that powered off or turned off cache bank will be used as a thermal buffer, and more thermal buffer will definitely reduce your temperature on chip. It will reduce your average chip temperature as well as it will reduce your peak temperature of the chip, right? So our cache-based policies are, we have also compared it with the greedy DBS policy that was developed earlier by some lab in Purdue University in US. Well, so these are the couple of algorithms that I have implemented earlier during my PhD. So that is for on the left-hand side, we have the algorithm that we have implemented for the HB, that is the hot bank. Hot bank were turned off. Hot bank practically were the banks which have the heavy temperature just because of the adjacency to the hotspot of chip, and we're just going to turn them off. On the right hand side, we have the CB, that is the cold bank. As I told, cold bank are not actually cold, they are rather they have the least usage. So you just turn them off to get rid of the some temperature issues. And finally, we got the results like this. And on the left hand side, you can see for the body 16 benchmark, and on the right hand side, you can see the results for the frag benchmark. And this benchmark is actually collected from the Parsec. I skipped that part in the simulation slide. So Parsec is a benchmark suite that I have used for all of my experiment earlier. Even also now I'm using Parsec and Ligra together. So Ligra is also another benchmark suite. They are very well known in the computer architecture community. Well, and they are multi-threaded, and sometimes also we have just used some thread binding techniques on the codes, as well as we also make them the multitask or multi-thread or multi-processing task as well. So we build them up during simulation. So the peak temperature and the average temperature for both of these temperature statistics, you can see our misbenefit is also very significantly high, and GDBFS has the least reduction in average temperature with respect to our policies, cache-based policies, and GDBFS is not at all a stable, maintaining a stable temperature of the chip. Maybe it peak, maybe it average. But our cache-based policies, they're both HB and CB, they are maintaining a stable temperature on chip in both cases for peak temperature as well as for the average temperature. But in this case, you can see the peak temperature reduction is more in case of GDBFS, just because of it actually targeting the cores. That's why the peak temperature reduction is more. But in case of our cache-based algorithm, the peak temperature reduction is not up to the mark. But definitely, it's comparable with the GDBFS policy. This is a special thermal variance that I have generated from the hotspot. So you can see the 16 tiles here. It's not at all much visible on this diagram. I don't. Okay. From here you can see that this is the results. I'm just going to the results. So here you can see the performance degradation is more in case of GDVFS in all these cases, whereas our cache-based policies, they are well enough, especially when we have the larger caches. I had also result for 16 MB, just I skipped this one here. So 8 MB, you can see the average temperature is really very, very good in our case. Additionally, we are also providing the stable thermal status of the chip in case of peak temperature as well as for the average chip temperature. For the GDVFS, we had the average chip temperature reduction of 3.3 degrees Celsius, but peak temperature reduction is a bit higher, that is 5 degrees Celsius in both in case of 4 MB as well as for the 8 MB caches. But the thing is that they are not maintaining the stability. So thermal stability is not maintained in case of the GDVFS. That was the drawback of the GDVFS. Well, so our summary is like that large LLC will consume more leakage, and Dicer actually strings the LLC to reduce the leakage as well as the temperature, and hotspot reduction versus leakage was our main target in this case. And both HB and CB show the sound improvements. And Dicer in LLC can therefore be used for the thermal efficiency as a supplementary method in addition with the DVFS at the cores. So Dicer for temperature control in centralized LLC-based CMPS. So how we have done this? So our primary objective was to control the cache temperature. Additionally, we are going to reduce the temperature of the global hotspots on chip by governing the on-chip conductive heat transfer. Practically, we are going to exploit the superposition and reciprocity theorem of the heat transfer to increase the conductive heat transfer at the turned off portion, right? So the contributions in a nutshell is like that. Initially, we have developed an analytical model for our architecture because this time for our centralized architecture, we had 64 number of banks. So to get to run some heuristic algorithms on this process was not at all very good because it may not give us very good results. So initially, what we have done, we have done some empirical analysis, and from there we framed some analytical model for our cache, and finally that outcomes of that analytical model we have used in our experiment to determine the optimal cache size that we can use for our underlying applications, right? And while turning up the cache banks, we followed 3 patterns. One is altro, and there is chase, and there is opter. So altro, practically here you can see on the left. On the left, you can see the altro where alternating row will be turned off and on, right? And here, 50% banks you can turn off. The black represent the prospective banks that will be turned off. On the other hand, if you look at the chase, it follows the pattern of a chessboard or checkerboard pattern, where at max you are allowed to shut down the 50% of the cache. But in case of opter, what we have done, we have just breaking them the whole structure into 16 groups. Each group contains 4 banks. Now, inside each group, you will have the target, and at most you can shut down 75%, that is 3 banks. So remaining 1 bank will be turned on to handle the request that will come to the remaining 3 as well as to its own, right? So this will handle the request of all the 4 banks of the same group. So that's what was the concept here, and why we have done turning off of the all banks at the periphery. So idea is that our hotspots is on the core of the chip. So the cores were at the periphery in this baseline architecture. So the all peripheral banks, if we can turn them off, so they will generate thermal buffer close to the cores. Thus, the core's peak temperature will be reduced. So that was the primary idea for this software. So this is the algorithm. So I'm not going into the in-depth analysis of this algorithm because it will take much time. So practically, thus it will work. So in case if you're interested, so you can definitely go through my papers, and as well as you can just send me email or just contact me. So I'm ready to discuss with you at any point of time about this one. So this is the results that we have achieved, and this is the spatial change in temperature with respect to GDVFS. So the same algorithm also we have used here, that is developed by some of the researchers in other universities. We compared their work with us. That's a core-based policy. And both GDVFS and opter shows the maximum reduction in peak temperature is 6.6 and 5.5 degrees Celsius for an 8 MB cache in this case. But standard deviation of the temperature is more in case of GDVFS in terms of peak as well as for the average chip temperature than ours, just because of its more fluctuation in temperature. Because you cannot keep the cores for a longer time in a lower voltage voltage or frequency settings, because you need to come up with the higher values to maintain the performance, right? And thus, and additionally, GDBFS has some considerable impact on the performance. And to maintain a lower thermal profile, cache-based policies are more effective than GDBFS in terms of stability, especially, right? So that's how I will conclude my PhD work. So here on the left-hand side, you can see the leakage minimization, where we have minimized the leakage power consumption of the caches and the whole chip by turning off banks and turning off OS as well. On the other hand side, you can see the significant reduction in peak temperature as well as average temperature were also achieved by applying these couple of techniques for the tiled CMP architecture as well as for the centralized LLC architecture. We said both leakage as well as the temperature. So that's how my thesis was framed. Now I am jumping to the core-based policy that I have been working since January 2019 here in Trondheim, Norway at NTNU. So the primary idea is that we are going to utilize the misses, practically the off-chip accesses that we are getting during an execution, because off-chip accesses are very much costly, and just because of off-chip accesses, your code will be in stall mode, right? So once your code will be stalled, we are going to reduce its VF settings, that is voltage and frequency. And towards that, you have to use the on-chip voltage regulator that is faster enough, and it can regulate your voltage by employing some VCO or voltage control oscillators, right? And towards that, you have to analyze something. First of all, if your code is an in-order code, so what you can do, at each and every memory stall, the code will also be stalled. But for out-of-order codes, it may not be true for each and every memory off-chip accesses, because out-of-order code can dispatch and issue an instruction from the instruction queue, which is actually not dependent on the current instruction. So towards that, what we have developed a 2-bit stall predictor for the out-of-order codes, and we have used a TLC called tagless cache that will actually detect the miss in early enough, so your miss delay span will be more. So we will have the more span for applying a GDBFS. So I'm not going to very details of this work because still this paper is under review. And we named this problem as WaFFLe. So, and this work actually provides us for a heterogeneous chip. We have achieved up to 8.5 degrees Celsius reduction in peak temperature and 6 degrees Celsius reduction in average chip temperature, while our performance degradation is less than 3%, that is 2.7%. Now my ongoing and future projects. So I am currently working on 3 basic projects. So first one is the 3D CMPS. For that, what I'm doing for 3D chips, thermal issues are actually one of the most significant problems to reduce, and it's kind of challenging task for the researcher and architects nowadays. And towards that, we are also working in thermal and energy efficiency 3D CMP building, and that will be an enhanced part with the cores, caches, and NOC. NOC is practically called the network on chip, and this work is in progress. That's why I put the WIP, work in progress. And another 2 work actually I am also doing with the other people at the University of Essex. I am working in temperature reduction in approximated real-time computing paradigm, and also my collaborator at the IIIT Guwahati. Some of my students are working there along with some of the professors at IIIT Guwahati. That is the thermal management in heterogeneous multi-core scheduling. And for the first one, I am collaborating with the Cyprus University of Technology at Cyprus, Europe. For my next project, Tectonic, so I'm planning to kick it off on January 2021, and I'll be working in this project. And this project actually spans over compilers as well as some advanced architecture, as well as some advanced hybrid cache architecture, where I'll also considering the NVMs. That's called actually non-volatile memories. So that part actually I'll also handle here. And the major motivation was to manage the temperature of the chip, and also we'll also be starting some sort of activities of the NVM when you will have the high temperature. Here are my publications. So all of these actually I published during my PhD, and my references are here. So thank you all. So I'd like to get some questions from you now.
Thank you, Shounak. It was very informative. Thank you. And few questions we have got. And in the catch bank usage in execution, So we have got different epochs running from epoch 1 to 4. When running all these epochs from 1 to 4 itself, will it not involve more competition, or will it not involve more energy running the epoch itself?
So I got a question actually. I'm not able to see you all. So just sorry for this one. So
Your screen is still shared, sir. If you remove that, you will be able to screen. Yeah.
well, okay. So, not able to calculate from here. So yeah, well, so yeah, I got your question. So the primary thing is that the epochs actually we have done some offline analysis on that. So first we have we ran actually 4 or 5 I think benchmark applications there, and suppose we ran them up to 200 millions of cycles. So then we just collected the traces of the cache. So there is no direct involvement of the computation here. So we just offline. In offline, we have analyzed that how many accesses are there to the cache banks actually, right? So there is no direct relation for the computational overhead or something else. So each and every epoch, probably I think that time I have taken it for the 30 or 35 million cycles, like that. So for the first 35 million cycles, this was the cache accesses for each bank. Then for the next 35 million cycles, we had this much of accesses, and so on. Like that, we proceeded.
Okay, nice. And in this turning on and off, this cache resizing, static and dynamic resizing, my basic question is, when performing all these processes, will not be there data leakage?
No, we have prevented that one because suppose the banks you are going to turn off, they have least usage, right? But they still have some data. Your point is very nice. So when you have some data, you need to maintain them, right? So for that,
Yeah.
you just send them to some other bank that is called target, right? Right?
Yeah, yeah.
Now target will also have its own data. So how to
Yeah.
manage? So where inside the target you will place them? So while placing them, you have to use the mapping techniques, basic mapping techniques. So mapping we haven't changed. So you just put inside the bank. So bank has its own mapping technique. It will map to some set, but those sets have some data. So for that, what we have done to get the eviction of that particular, if your set is full, you cannot put the migrated data there, right? Then you just, we have used some techniques for reuse counter there to resolve this problem. So the more LRU data will be evicted from the total cache system, and they will be returned back to the memory. Right?
Okay. Yeah.
So incoming through migration and your current data at the target, both will be compared and their LRU will be sent back. Practically in real system, you cannot implement LRU in cache, right? So that's a big bottleneck. So we have implemented in the simulator, but you can definitely use the same technique for the NMRU caches as well, where you cannot write some MRU data back to the memory, but you can definitely do it for the other most recently used data. Yes.
Yeah, that's what, because we use cache resizing, we use data like that. That's what my mind is totally traveling towards the cyber security with respect to data leakage. That's why.
Yeah, it's a really relevant question. Yeah. So reuse counter, you can find the details in some of my references as well as in my paper as well. So just go through them. Surely you can get that more details.
So is one more question.
Yeah.
Related to cache. You are comparing cache policy with GDVFS policy. Who you are comparing with this? What about other policies are there?
Well, so most of the thermal management techniques so far developed, they actually targeted the cores. So I didn't get enough literature that time with which I can compare my own policy. So thermal management is actually made for the cores always. So almost over the couple of decades. So since when the thermal issues came up in the picture, and the researchers and architects, they mostly target the cores to reduce the peak temperature as well as for the average chip temperature. So I had to compare with the core-based policies to be in the line, right? To be in the streamline to show that cache-based policies are also useful enough, like the core-based policies. But definitely, it will not effective to reduce the peak temperature. But average chip temperature can be reduced additionally with the peak temperature. So we didn't have enough literature with which we can compare for the cache-based policies.
when you are comparing, which one is the best?
So it depends actually. So best thing is that you should apply both together. So core-based policies will definitely reduce the peak temperature, whereas cash-based policies are best for reducing the average chip average chip temperature, right? So if you club them together, you are going to get the more benefit. So core-based techniques will be the primary thing, and you are adding some supplementary with the cash-based techniques. So together they can do the best thing, right?
The temperature will lead to positive correlation or negative correlation?
Regarding what?
Any temperature improvement, temperature hike
It will reduce the temperature. It will reduce the temperature.
Okay.
Yeah.
Okay. Thank you, sir.
Yeah. Okay. Welcome.
Alish ma'am.
Hello.
Yes, sir. Yeah.
So, hello, hi. I hope you can hear me. So, I have one question apart from the presentation. How is the experience in doing the postdoc in Norway? I mean, do you have any advice for the students who prefer for the masters there in Norway?
Yeah, definitely. So they can come here, and first of all, the technical things are pretty good here. So the infrastructure is well developed, and for almost all the labs, we have very good industry collaboration as well. And for collaboration perspective with the other universities also, you have lots of opportunities here, and all nearby labs are also equipped with good infrastructures, especially in Sweden. Means other than Norway, also nearby Sweden is there, Denmark is also there, so lots of good labs are here. So you will have the more exposure to industry as well as the other research labs. So for masters they can come, and for Norway, one thing is that the means cost of education is almost free. So that's a pretty thing here. So almost for the all Scandinavian countries, I think. So they can surely come and join.
But the problem our students are facing the living cost, right? Living cost is quite high there.
Quite high.
Yeah, so that's the problem my students face. That if I tell them suggest to go to Norway, a Scandinavian country, they're afraid like the living cost is too much. So how do we manage? And do you have any special advice for that? How to manage the living cost? Of course, if they go for the scholarship, it would be helpful for them.
If you come with some scholarship, then it will be very, very much easy for them to manage the living cost here. Additionally, people also do some part-time jobs here as well in Norway, so who are doing masters and who are from the Asian countries or Africa. So they are doing this kind of jobs, means in part-time here to cope up the situation. So living cost is really a big trouble here.
Yeah, that's true. Yeah. Fine. Thank you.
Yeah, welcome.
So, Dhanlakshmi man and Krishnamurthy sir, is there any more questions?
No, sir. No more questions.
Fine.
So I didn't make you bored, right?
So, no, it was really interesting.
No.
It was really good. Fine. With that, I'll give the oath of thanks. On behalf of KCG College, I'd like to take this opportunity to propose oath of thanks to who have directly or indirectly contributed to this webinar on modern computing, energy versus performance, organized by our institute. First of all, I would like to thank the resource person, Dr. Shounak Chakraborty. We are really enlightened with your knowledge and presence, and you give a valuable advice for your students regarding the postdoc and masters. And I also extend my thanks to Dr. Krishnamurthy, Head of Computer Science Department, and Dr. Dhanlakshmi, their enormous cooperation in organization of the event. I would like to thank our principal and associate dean for their enthusiastic support, and a special thanks to professor and students for the active participation. With these warm words and kind message, we move to the end of today's webinar. Thank you all for participating, and thank you. Hope to see you again. Resource person. Yeah. Bye.
Happy to see you again. Yeah.
Yeah.
Okay,
sure.
nice to meet you
Thank
all.
you. Yeah. Bye.
Thank you. Thank you, Shounak.
Thank you all.
Yeah.
Bye. Thank you.
Bye.